Okay, so in this video, we're just going to recap the 4 HL mechanisms, the ones that all use curly arrows, to try to highlight some similarities and differences that you should really keep in mind. When you are getting scored for these mechanisms, the key thing really is the curly arrows. Also, the other key thing would be what structure exists in the middle of the mechanism. So for 3 of these mechanisms, you are going to have 2 steps. So SN1, electrophilic addition, and electrophilic substitution. These 3 mechanisms all have 2 distinct steps. SN1 is the only one that is a one-step mechanism. And so the one-step mechanism means that you don't actually show an intermediate, you show a transition state. Every other mechanism is 2 steps. And so every other mechanism has an intermediate rather than a transition state. And that intermediate in every one of these mechanisms is a carbocation. So that's really nice to lock onto. I'm not going to write it again, but I'm just going to put a check and a check. Okay, so in terms of our drawings, the transition state is the one that has the partial bonds. So in SN2, you get the 3 things attached to the carbon, and then you get the partial bonds where you've got the halogen that's leaving, and you've got your nucleophile that is attaching. And this thing has a minus charge. So this is what the transition state looks like. In the other ones, you always have a carbocation. And so carbocation in SN1 looks like a trigonal planar carbon atom with a positive charge. In electrophilic addition, there's a lot of emphasis on the carbocation, and the major product is the one that comes from the more stable carbocation. So when you're drawing the carbocation, generally you're trying to focus on making the carbon that is surrounded by the most other carbons. So like this, for example, would be a tertiary carbon. That is the more stable carbocation because those neighboring carbon atoms are able to donate negative charge, and it stabilizes the positive charge on that carbocation intermediate. So you're trying to have the carbocations that are most central, surrounded by the most other carbons. It's not always going to be a tertiary one. This is one example I'm choosing to sketch out right now, but that was just a review for electrophilic addition. So in this one, you have a little extra details to remember, thinking about the major product and the most stable carbocation. This mechanism is probably the trickiest because you have the alkene that's donating the electron pair, and you have to choose which carbon becomes the carbocation. And so that's where that idea of the most stable one, the one that's surrounded by the most other carbons, will be the most stable. In the electrophilic substitution, you're starting with the benzene ring, and the carbocation is when the benzene ring, the delocalized ring of electrons, is temporarily broken, so it becomes dotted, and you have a positive charge near the carbon atom here at the corner. At this point, you generally have the hydrogen as well as the electrophile. So at this point, the benzene ring has already donated an electron pair to attack the electrophile, and the electrophile has attached, and now you're left with this benzene ring carbocation. So that's a real key distinction between the different mechanisms, and so really the standout here is the SN2, the transition state versus the carbocation. The other things that we'll see, the 3 substitution mechanisms, SN1, SN2, and electrophilic substitution, all have 2 arrows. So the ones that are 2 steps involve 1 arrow in the first step and 1 arrow in the second step. Remember that the arrows are always going to show like electron pair movement, or they're going to show bond breaking. So they're going to show bond forming and bond breaking. You need to make sure that you always start those curly arrows from electron pairs or from bonds, and then they go to atoms. So they show the formation or breaking of bonds. Same goes for electrophilic substitution. In SN2, you're going to have both arrows in the same step because it's a one-step mechanism, but the arrows still show bond breaking and forming. In electrophilic addition, you will have one extra arrow because you're going to have the arrow that comes from the carbon-carbon double bond, the pi bond, that bond breaking, and then that's showing a bond forming. You have to show the bond breaking in either the Br2 or the HBr or the water, whatever is being attacked. And then later you have to show the extra thing attached back on. So addition, I think, is that you're going to see two arrows in the first step, and then you're going to see one arrow in the last step. So addition to me is the trickiest one. There's a lot more nuance to it. There's more arrows. There's more decision making you have to make. There's more options within the mechanism itself, so it's definitely worth some review. Otherwise, make sure you know how to draw those arrows, where they start and where they point to is really important. How to draw the carbocations or the transition states is really important. Those are most of your marks. The last mark in these is generally having the correct starting and ending structures. So like the correct reactants and products, or with SN1, SN2 having picked the correct mechanism to show if that's relevant for the question. But out of 3 or 4 marks, 2 or 3 of the marks is going to be the curly arrows and the thing you draw in the middle. So this video recaps and highlights what those things should look like, how many arrows, etc.